All right, so let's keep going here. We're talking about, remember, these transition metal complexes. We take our transition metal ion and they will bind these ligands to them, creating these new coordinate covalent bonds. We spent a lot of time talking about how to name these compounds, as well as doing some review from Chem1A about how we figure out what the electron configuration of that central metal ion is. All right, and now we're going to put that electron configuration into good use, talking about kind of like the properties of these complexes here. All right, so first of all, you sort of were introduced to this theory of how covalent compounds work last semester, what was called Vesper theory. All right. And really what y'all did was you learned how to draw Lewis structures, and then you figured out what the shape of those Lewis structures were by applying that Vesper theory. And that was kind of the extent of to which you were introduced to it. Turns out that that Vesper theory is a quite intense mathematical theory that kind of underlies these covalent compounds and how their bonds work, all right? You're just kind of scratching the surface at this point. It turns out to be this big math theory and stuff like that, so you cover it a little bit more, revisit it when you get to higher level chemistry. So anyway, that's like this theory about how covalent compounds works, that Vesper theory, all right? It turns out that Vesper theory doesn't really work for these transition metal complexes. It works a little bit, but not all the way, all right? So what they did was they said, all right, these transition metal complexes, they have these covalent bonds, but we're going to call them special coordinate covalent bonds. And in addition to explaining them with Vesper theory, we're going to tack on this new theory, which is called crystal field theory. All right, and so that's what I'm going to introduce to you all here today, this crystal field theory. Okay, and again, just to kind of summarize what I was saying, these transition metal complexes, they have these shared pairs of electrons. What we call covalent bonds. All right, but these complexes do not behave like normal covalent compounds. All right, the bottom line is they're kind of the same, but a little bit different, right? So we have this extra little theory that we're going to talk about that helps explain those differences. And that's exactly what this crystal field theory is going to help us do. It's going to help us understand the differences between these transition metal complexes and other covalent compounds. All right, in particular, it's going to help explain two properties of these complexes. The first being their magnetic properties. All right, by that I mean why these complexes interact with the magnetic field. All right, typically we think of magnetic properties as belonging to metals. All right, covalent compounds do not really interact with magnetic fields, and yet we have this covalent-ish compound, and it seems to be interacting with magnetic fields. So why is that, right? So that's one thing that this crystal field theory is going to help us to explain. Okay, and before we move on, I'm going to use this opportunity to introduce some terminology here. We call something paramagnetic meaning that it does interact with a magnetic field. And it interacts with the magnetic field because it has unpaired electrons. Okay, we then use the term diamagnetic. For the flip side, for compounds that do not interact with magnetic fields. And that's because they have no unpaired electrons. And that's kind of going to be our goal, is to look at a complex and be like, all right, that complex is diamagnetic or that complex is paramagnetic, right? So we got to be able to tell whether they have paired electrons or unpaired electrons. Okay? So again, we have this crystal field theory, this kind of tag along to the VSEPR theory that's going to help us explain these transition metal complexes. And there's two properties that's going to help us to explain. First, the magnetic properties of these complexes, whether or not they interact with the magnetic field. All right, and the second part that it's going to help us understand is the color of these complexes. All right, so what do I mean by that? I mean simply that these transition metal complexes, they tend to be very brightly colored. Okay, and we'll actually sort of save this part of the crystal field theory for next class period, but just to kind of point out, like, this is a series of transition metal complexes all made with the same transition metal ion, cobalt-3, just with various ligands. And you see that they take on this kind of rainbow spectrum of different colors here. So this is one of the things that we're going to be able to better understand, is why we get such pretty little colors when we make our transition metal complexes.
Is that unusual for other covalent compounds?
Yes. So other covalent compounds tend not to be brightly colored. There are a class of organic molecules we call dimolecules, and those are very brightly colored. But we know why, and they have these very distinct structural features of having a lot of carbon-carbon double bonds, like all in a row, like 15 carbon-carbon double bonds in a row means that this thing's going to be red, or something like that. Some really definitive structural features that these definitely do not have, right? They don't share that same structural feature. So yes, we do see color in a small class of covalent molecules, but we know why, and it's definitely not the same reason why these things would have color associated with them. So yeah, that's a good question. Cool. All right, so really what we're going to focus on today is this magnetic properties business. All right. Okay, so first of all, we're going to have to talk about the geometry of these transition metal complexes. We're going to kind of have to lay some groundwork, and then we're going to bundle it all together here to finally get at that punchline of the magnetic properties. Okay, so our transition metals, they fall into one of four buckets in terms of their geometry. All right, they can have this linear geometry. where we have our central metal ion sitting in the middle, and those two ligands are on opposite sides, as far away from one another as possible. We saw these geometries in Vesper theory as well. We got a little bit smaller of a subset that we're going to see with our complexes, but yeah, we're going to repeat a lot of the same ones. All right, there's also this fancy geometry here called a tetrahedral. Okay, and if you have one central metal ion and four ligands, and you're trying to arrange them evenly in space, that's how you would get this tetrahedral geometry. This is a geometry where everything's perfectly spaced out. All right. It's a little bit more rare, and we'll talk about why and when we see it when we get there. But there's also another geometry. If you have four ligands, they can instead be oriented in this square planar geometry. All right, we see this square here. All four of those ligands lie in the same plane, hence that name square planar. All right, again, making a little square around that central metal ion. All right, and then the last one is if we have this geometry of what's called octahedral. All right, that's if we have this central metal ion and we decorate it with these 6 ligands. Whoops. All right, each one of them are 90 degrees from one another, kind of evenly spaced out there. This is just a fun fact here, but does anybody know why it's called an octahedral, even though there's only those 6 ligands? Because it has 8 faces, exactly. Like if you imagine it instead like a die that you rolled on the table, it has 8 triangular faces that connect it. Yeah, exactly. Cool. All right, so these are these geometries of our transition metal complexes. At least these are the most common ones, the ones that we're going to talk about. All right. And it turns out that these correspond to what's called the coordination number of these complexes. Okay. So coordination number, I've sort of drawn it here how many ligands there are, but remember we also have these polydentate ligands, these ligands that can create more than one of these coordinate covalent bonds. So our coordination number kind of simply takes that into account. The coordination number is the number of ligands, but also multiplied by the number of donor atoms per ligand. Right, and that's how we're going to calculate it based on what our ligand is and what the formula is for our complex. It corresponds to the number of coordinate covalent bonds. All right, if we have a coordination number of 2, that's how we get that linear geometry. If we had a coordination number of 4, we could either have a tetrahedral or a square planar geometry. And if we had a coordination number of 6, we would have an octahedral geometry. All right, so what we're going to see is we're going to be given the formula for one of these complexes. We're going to have to figure out what its geometry is. And so we're going to calculate it based on the number of ligands it has and the number of donor atoms that those ligands have, right? So our goal is to work from this complex formula here in order to figure out what our geometry is. Again, that's going to correspond to that coordination number. And we can calculate that coordination number because it's the number of ligands times the number of donor atoms per ligand. Cool. All right, so let's get an example going here. All right, so we're going to look at this crystal field theory for these. I'm going to leave it blank for right now because I don't want to give away the punchline complexes. All right, one of these specific geometries, but I'm going to make you all tell me what the geometry is. All right, so we need a formula for a complex ion here, or for a transition metal complex. Yeah, complex ion. All right, and there's a few things that we learned how to do last class and this class. So, step 1, you're going to give me the oxidation number of this complex. I also want that new coordination number for this complex. And then just for fun, to put our skills to use from last class, we're going to name it as well. All right, so in a second, I'm going to give you a second to copy down what we're looking for here. I'm going to then put this complex formula on our constants page so you can give me these pieces of information here. All right, let's get rid of all this business. All right, this was FeCl6 minus 4. Again, we're looking for the oxidation number, the coordination number, and its name. All right, so based on what we learned how to do last class, everybody tell me these 3 pieces of information here. No, that'd be what we call the net charge. The oxidation numbers are pertaining to each particular element, and in particular in this chapter, I'm always focused on the transition metal. Yeah, and we're also going to need it for another important piece of information here.
Is it the donor atoms, because obviously there's 6 chloros, so it would be 6 donor atoms or just 1?
Okay, so there's 6 chloroligands. Each one has just 1 donor atom is how we would say that. Donor atoms are per ligand.
So for the coordinate number, we would put 6 times 6?
You would do 6 times 1.
Times 1, okay.
Yep.
Do you have to use the, I don't know how to pronounce it, sorry if I butcher it, but polydentate ligand?
Okay, so that's a good question. We have 2 sets of prefixes, monodentate and polydentate. So first of all, let's just pick apart the prefix part, mono being 1, poly being many, right? What does the dentate part mean? Does anybody remember what the polydentate ligands were?
It's the ones that have multiple donor atoms?
The ones with the multiple donor atoms. These are our polydentate ones. So for these, we would have to look at this column here. For all the other ones, we'll look at this column here. right, my oxidation number. My iron plus my 6 chlorines have to equal that net charge of -4. I don't know what my iron is, but I know those 6 chlorines each have a charge of -1 based on my ligand chart here. And so when I solve my equation, I get iron has a charge or an oxidation number of +2. When I go to name this thing, remember these charts are just in the exact order that they need to be in our name as well. So we have the number of ligands here, 6. So we're going to use that prefix hexa. Those chloroligands. And then when I get to my metal ion here, when I get to my metal ion, I got two halves to this chart here, metal and anion name. Which one am I going to use? Yeah, because this is going to correspond to the net charge of that complex, which is negative. So I'm going to use iron's cool anion name, ferrate. So that would be hexachloroferrate. And then finish it off with that oxidation number of 2. All right, so then if we have a coordinate number, this is the number of ligands times the number of donor atoms per ligand. Well, I have 6 of those chloro groups. Each one has just 1 donor atom. So that means I have a coordination number of 6. Cool. All right, so just to go back and summarize here, not from the very beginning. All right, we got an oxidation number of +2, a coordination number of 6, and we said this thing was hexachloroferrate 2. Okay? Cool. So, 2 other important things that we need. One coming directly from the oxidation number. We're going to need our electron configuration in order to keep this further our analysis here. And our coordination number, we know, tells us what about this complex? Its geometry. All right. So first of all, for a coordination number of 6, what's my geometry going to be? Octahedral. All right. So now we can title this thing off. We are specifically looking at our crystal field theory for these octahedral complexes. We're going to see that the geometry has a pretty big impact on our analysis here. All right, for our electron configuration, I'm specifically talking about the electron configuration of that iron 2 ion, of that central metal ion. All right, so let's just go to our periodic table somewhere. Here's a good one. All right, everybody take a second and tell me what the iron and then iron 2 electron configuration is. And you can feel free to use that noble gas abbreviation, make our lives easier. All right, so quick cut here into these blocks. First two are the S block. Back chunk is the P block. And our transition metals live in the middle here in the D block. All right. The next most important thing in this sort of process is the numbering of these rows. For the S block, there's nothing crazy. You just start numbering down at 1. But for the P block, I'm going to have to remember to start numbering at 2. And for the D block, I need to start numbering at 3. So iron lives in that 3D row on my periodic table. All right, I'm going to use my noble gas abbreviation using argon. That gets me all the way up to this point here. Now I got to include that extra bit for iron. That's that 2 4s electrons, as well as these 1, 2, 3, 4, 5, 6 3d electrons. So 4s2, 3d6. And now if I'm going to do the electron configuration for my iron 2 ion, I got to start scratching electrons from my atom's electron configuration. And which two do we pull first? We pull the S first. So that will leave iron ion with just 6 3d electrons, as well as whatever argon's got, all its core electrons as well. All right. Where are we? Cool. All right, so filling this out now, our electron configuration, argon 3d6. Awesome. All right, so now we have all the information we need to move on to the next step in this analysis here, which is to draw these electron configuration diagrams. All right, I'm going to leave a little bit of space here so that I can do my electron configuration diagram for this particular complex here. All right, I'm going to kind of like just do an example of what the heck I mean by an electron configuration diagram real quick.
Is it like the lines with the level, the energy level?
The boxes with the arrows and stuff, yeah. All right, so first of all, if we did our electron diagram, all right, so first of all, oxygen, looking at our periodic table, we would say is 1s2, 2s2, 2p4. All right, you can trust me on that one. If we're going to turn this into an electron configuration diagram, we're going to represent all of this exact same information here, but we're going to do it on a little graph. All right, we're going to create this y-axis of increasing energy, and we're going to represent our orbitals here with these little boxes. So this box here represents my 1s orbital. That's the lowest in energy because it's all the way out front here of my electron configuration diagram. My next orbital is going to be my 2s orbital. All right, and now I need to do my 2p orbital. But that p subshell can fit a total of 6 electrons in it. So it actually is composed of 3 of those peanut-shaped orbitals. Each one just has a different orientation in space. So I need 3 boxes to represent the 2p level here. All All right, and now I want to fill in with the proper number of electrons. In that 1s orbital, we have just 2 electrons. Each box can fit a maximum of 2 electrons, but those 2 electrons have to have opposing spin. Right? One of these weird properties is that electrons are spinning around like tops, and the only way that they can share an orbital together is if they're spinning in opposite directions. So we represent that one as a spin up arrow, the other as a spin down arrow. Same thing with my 2s box. Boom, boom, spin up, spin down, because it's got 2 electrons in there. All right, but now I got to this 2p subshell here, and I got 4 electrons. And remember, there are some weird filling rules for these diagrams. First, you always go top to bottom. Second, you can only have 2 electrons in a box, but they have to have an opposing spin. The last one was when you get to orbitals that have the same energy, like these here, you actually go through and half fill everything first before going back and doubling up. All right. So this would be my electron configuration diagram for this oxygen atom, kind of conveying this same bit of information here. All right, so now we want to do the same thing, but for our transition metal complex. First of all, before we move on, let's note our s orbitals have 1 box. The p orbitals have 3 boxes. How many am I going to draw for the d orbitals? 5 boxes. All right, cool. Which is important because that's what our transition metal has here. All right, so first when we do our electron configuration diagram, we're going to do it for the iron 2 ion when it's all by itself, before that complex is formed. All right, so here's my y-axis of energy. Okay, we're going to be lazy and do our noble gas abbreviation of our diagram as well. So down here at my lowest energy, I'm going to say whatever the heck argon's electron configuration diagram looks like. Fill in that first. Right, just like before, this means insert argon's electron configuration. So now I just need to represent the 3D subshell here.
If we were to do the full thing, would we just not include the 4s, or would we include it and not fill it?
Yeah, you would just not include the 4s.
Okay.
Well, I mean, I say that. It is there, but it is empty.
So, okay, so we would, like, draw the box, we just not fill it?
Yeah, I have to say, there's this weird thing that happens when orbitals get filled where their energy levels kind of shift a little bit. And so the 4s turns out to be more like right up here, a little bit higher. Once there, it's a complicated thing. I don't want to dive down. I lied. I don't want to go down that rabbit hole. Anyway, some weird stuff happens when you start filling stuff up in terms of these energy levels. But it is true that all those orbitals do exist. They're just empty. Okay, so everybody take a second and fill in this electron configuration diagram then. How do I fill this in with the proper number of electrons? All right, first of all, how many electrons are we putting in there to begin with? Our 6, because of our electron configuration, right? That's why we had to do all that work to get that electron configuration, so we could know how many electrons to put into our little diagram here. All right, so now I have 1, 2, 3, 4, 5, 6, right? I'm going to go through and half fill everything first before I start doubling up. So this is what the electrons would look like in an iron 2 ion when that iron 2 ion was just floating around in space all by itself, right? But we don't care about that. We care about our iron in that iron, that hexachloroferrate compound. And our goal is to build the same thing here, our electron configuration diagram, where we put boxes and we fill them in with electrons. All right, but what we're going to see is when we start decorating that iron ion with ligands, all of a sudden something funky starts to happen with the energy level of these 5d orbitals. When iron ion is all by itself, they are all the exact same energy. All right? As soon as we start sticking these ligands around it, these energy levels of these orbitals are going to change. They're not all going to be the same energy level. All right? So first of all, let's remember the whole basis here is that our ligands are what? Electron rich or electron poor? Those are the electron-rich ones, right? Because the central metal ion itself with its positive charge is electron poor. It's attracting those electron pairs from the ligands. All of our ligands are pretty electron-rich ligands, okay? So, where's my pretty figure here? Dang it. Oh, okay. All right, so first of all, ignore the green part for a second. Let's focus on this little yellow balloon thing in the middle here. All right? Let's remember that our d orbitals, they have those daisy shapes, right? So this is this daisy-shaped d orbital here. And if we looked at the difference between, there are those 5, right? If we looked at the difference between all of them, they have that same kind of daisy shape going on. They're just oriented differently in space. So one of them's facing this way, the other one's facing that way, the other one's facing that way, another one's facing diagonal, right? They're just oriented differently in space, these same daisy shapes here. All right, this is another one. It's kind of oriented differently in space. There is one weird one. All right, there's one that looks a lot more like a p orbital, but then it's got a little donut around the middle. So in Chem1A, we say, remember, d orbitals, they look like daisies and the weird donut one. All right, it's just a simple thing to kind of keep in mind about the shape of these orbitals. Okay, and again, when the ion is all by itself, all of these orbitals have the exact same energy. First of all, where did these orbitals come from? Who came up with the daisy and the donut business? Yeah, it's all the math equation, right? It's not like anybody was like, I bet it looks like a donut, right? That's not what had happened. They did this big, ugly math equation. They solved it, and these are the shapes that came out of it, right? So anyways, that's why we got these funky-looking shapes here. All right, so what happens is now we're going to start decorating it with these negatively charged ligands, right? And in this octahedral geometry, we're going to put 6 negatively charged ligands around each one of those d orbitals. And what we're going to see is some of them are oriented in such a way where those negatively charged ligands and that orbital for my d, they fit right in between one another. And let's think about it. Do electrons in an orbital want to interact with these negatively charged ligands? No, why not?
Because they're negatively charged.
Yeah, like charges repel one another, okay? So, great, these two like charges, they dodged one another because the orbital fits directly between the ligands. But then there's other ones where those negatively charged ligands hit that orbital head on, right? We got this direct overlap between my orbital and my negatively charged ligand. So that weird donut one, for example. There's another one. If we lay the daisy shape on its side in such a way, we can see that in this one as well, we have this direct intersection between our ligands and that orbital. Okay? So the bottom line is some of these orbitals, they are sitting between those ligands, other ones are hitting them dead on. Well, because these like charges repel one another, these ligands, or rather these orbitals, are going to be higher energy than these other ones. All right, so what ends up happening when we decorate our ion with a bunch of ligands is what we call crystal field splitting. All right, where now these boxes are no longer the same energy, but we have 3 of our orbitals that are lower energy and 2 of them sitting at a higher energy level as a result of that direct overlap with the orbitals, the lobes of the orbital, and those negatively charged ligands.
And that corresponds with their orientation quantum number. That's why those two are higher because of the orientation.
Specifically because of the orientation. Yeah, I mean, I don't really care that you guys like know this, but they do have names. The weird donuts, the dz squared, and the one on its side is the x squared minus y squared, and those are the 2 that are higher in energy. You don't have to know that. You need to know that there are 2 high, 3 low. All right, 2 of them are going to interact in such a way that raises their energy, and the other ones, they don't have their energy raised quite so much. All right, so this is sort of what this full figure is showing us here is our 5 orbitals split into this pattern here where we have 3 low and 2 high. Where's my stuff?
Tag your
Oh, cool. Thank you. All right, so we have our electron configuration diagram. We have our splitting diagram here because we've decorated that ion with these orbitals. All right, importantly, this gap in energy here, we give this uppercase delta a triangle. This is what we call our crystal field splitting energy. All right, the difference in energy between those lower 3D orbitals and now our 2 higher 3D orbitals. Cool. All right, so now we want to fill this diagram in here with our electrons. So we're going to say filling our splitting diagrams. All right, well, in order to do this, we're going to have to turn to our constants page for this chapter. All right, we look at the bottom here. We have this spectrochemical series. So what's this thing doing for us? We see we got a bunch of our ligands, and they're ranked from lowest to highest here. All right, but lowest to the highest what? All right, these ones over here on the left, these have the smallest crystal field splitting energy. Right? Remember, our crystal field splitting energy is the gap between these 2 energy levels. So something over here would still form this same sort of splitting pattern of having 2 high and 3 low, but there'd be a much smaller gap between them. Right? A much smaller splitting energy for those small crystal field splitting energy ligands. And the ones on the other side, these are the ones with the largest crystal field splitting energy, which means that they have this same splitting pattern unique to our octahedral, but now there's a huge gap between those 2 energy levels. All right, so here's my small delta. Whoops. And here's my large delta.
And this doesn't have all of them on here.
It does not. Not all the ones we know how to name. All the ones I'm going to throw at you for this particular purpose, but yes. All right. So depending on how big that gap is, it's going to influence how we fill in our electrons. All right. For our small crystal field splitting energy, we call these high spin ligands. Those with small deltas. All right. If we have a high spin ligand, a complex with a very small crystal field splitting energy, we're going to half fill all orbitals before we go back and double up. All right, so what do I mean by that? Well, let's take our small crystal field splitting energy diagram here, fill it up in this high spin way. I'm going to start filling in these electrons. All right, but that gap in energy is so small that these electrons would actually go into this orbital all by themselves, then have to double up. All right, it's kind of like if you were in a hotel. These three rooms here are all the same price. So yes, you would obviously go choose those. Maybe this one's $1 more. You'd rather do that than have to sleep next to your friend, right? You'll pay the extra $1 to sleep in your own bed. Okay? That difference in price, that difference in energy is so small that they're going to half fill all of these orbitals first. On the flip side, we have our low spin ligands. These have a large crystal field splitting energy. All right, for these ones, we're going to have to fully fill that lower energy level before we move up. All right, so for this large crystal field splitting energy diagram, if I'm going to fill this in with 4 electrons, my first 3 get filled in the exact same because these boxes are all equal in energy. All right, but when I go to put that 4th electron in there, I'm going to continue to fill that lower energy row. All right, this box up here is way outside our price range. We're just going to have to bunk with one of our friends here down at the bottom. All right, that difference in energy is now so significant that that electron would rather pair up in an orbital with one of its buddies than move up to that higher energy level. All right, so this is our different filling that we have for our, depending on that crystal field splitting energy. If there's a small crystal field splitting energy, we would use this high spin way of filling in our diagram. If there's a large crystal field splitting energy, we would use this low spin way. All right. And our cutoff, we're going to kind of look at this spectrochemical series and give it a cutoff here. We're going to say that that's between ammonia and water, where over here are our high spin ligands, and over here are our low spin ligands. All right, and that's not exactly law, but it is a helpful cutoff to have. Okay, so then given what we just discussed, everybody take a second and fill in our electron configuration diagram properly. All right. Is chlorine, the chloroligand, a high or low spin ligand? It's a high spin ligand. So let me just kind of, with my diagram here, show that this is a pretty small difference in energy. So if it's a high spin ligand, I need to fill it in with these, how many electrons? 6. And I'm going to go through and half fill everything first before I would start to double up on my electrons. All right, so here's our electron configuration diagram for iron in our hexachloroferrate complex. All right, so now let's compare high versus low spin ligands. Here's my electron configuration diagram for this iron in our hexachloroferrate complex. Okay, so now what I'm going to do is I'm going to take the exact same metal iron. I'm going to create another octahedral complex. Same coordination number. But I'm going to swap out the ligands. I'm going to use one of those cyanoligands instead. And we want to create another electron configuration diagram, but this time for this new complex here. All right, so first of all, the splitting pattern that we see of 3 low energy orbitals and 2 high energy orbitals, that's going to be the same for all octahedral complexes. So since I got that same coordination number, I have that same splitting pattern here. But the difference is how close we should be drawing these 2 energy levels together. All right, so if we look, that cyanoligand, of course I lost it, is a low spin ligand. You can all trust me because I can't find it. I have 1,000 pages open here. Isn't it right here? Oh, duh. Okay. That cyanoligand. That's now one of our low spin ligands. So we have a very large crystal field splitting energy. So now I'm going to draw this with a very big gap between these 2. And we're going to fill this in with that same number of electrons because we got that same metal ion. But everybody take this and fill this in that low spin method. right, now I'm going to go through, but I have to fully fill this lower energy level before I'm allowed to move up. I guess I still got argon down here. All right, so this is our comparison here, where one of these is our high spin ligand, and the other one is our low spin ligands. All right, and then lastly, remember what the punchline of this was to tell us about the magnetic properties of these complexes. So everybody take a second and tell me whether this would be, either one of these would be diamagnetic or paramagnetic. Yeah, exactly. All right, so remember that terminology. Paramagnetic means it does interact with the magnetic field. Why does it interact with the magnetic field? Because it's got unpaired electrons. So this high spin complex would be paramagnetic. Our low spin complex doesn't have any unpaired electrons, so it won't interact with the magnetic field. It will be diamagnetic. All right, so again, crystal field theory was needed to help explain the magnetic properties of this complex, as they were really puzzled by why they would just change the ligand and all of a sudden it would change the magnetic properties, until they realized that there was this splitting happening of those d orbitals. All right, and depending on the size of that gap, we get different filling rules for our electrons. All right, cool. So we covered our octahedral complexes. We're going to kind of ignore linear other than to say they exist, but we are going to take a look doing the same thing for our tetrahedral and square planar complexes. We're first going to look at those tetrahedral complexes. All right, so for the sake of time, I'm just going to kind of kick this off here with our needed information. First, we need that oxidation number and that coordination number. All right, my oxidation number is +2 in this complex. The coordination number, this was something new, so let's go ahead. I'm going to give you a second here, given our constants page, this information that we would need to answer this. Everybody take a second. Tell me what the coordination number of this CO-CO32 -2 compound is. All right, remember, number of ligands times the number of donor atoms per ligand. There are 2 ligands, but each one of those carbonato ligands has 2 donor atoms. So I get that coordination number of 4. All right, we can also note just for fun here, since this is a polydentate ligand, we would have to use those polydentate prefixes bis. So this would be bis, and then in parentheses, carbonato. Remember, the parentheses are another weird part of those polydentate ligands. Bis, carbonato, cobaltate. 2. All right, so we got that coordination number of 4. Again, this thing was bis carbonato cobaltate 2. All right, so for right now, there are 2 geometries that would have a coordination number 4. As you probably guessed from the header here, this one's going to be the tetrahedral. For right now, you're just going to trust me, and I'll tell you how I know this when we get to our square planar complexes. All right, and the last thing we need is the electron configuration for this complex, which again, for the sake of time, I'm just going to note is argon plus 3d7. All right, and now we're going to play the same game with our electron configuration diagram. All right, you don't really have to put it down because it's going to look very similar to this here, just with a different number of electrons. So I'm going to steal this. Okay, if we did cobalt 2 alone, we would have these 5 equal energy orbitals, and we would just fill this in with these 7 electrons. But what we're really after is cobalt in our complex. All right, and just like before, as soon as we decorate that ion with those negatively charged ligands, we see this crystal field splitting. All right. And our crystal field splitting here, the pattern is going to depend on our geometry. All right, so if we go to our constants page here, we see that for octahedral, we always get that same pattern of 3 lower energy orbitals and 2 higher energy orbitals. For a tetrahedral, it's kind of flipped upside down. Now the 2 of them are lower energy and 3 of them are higher energy. All right, so we're going to make our little diagram here with our boxes, but now we're going to draw 2 of them low and 3 of them higher energy. And I want to fill this diagram in with those same 7 electrons. All right, but previously we ran into this problem with how do we fill it in? Is it a low spin? Is it a high spin? And for octahedrals, you have to go and you have to look at your ligand identity. Whether it's high spin or low spin depends on the ligand. Well, it turns out for tetrahedrals, since there's just less negative charge, right, less negatively charged ligands, and they're all evenly spaced out, our tetrahedral complexes are always high spin. That crystal field splitting energy is always on the smaller side.
Can you explain again why that is?
There's just fewer ligands, right, as opposed to an octahedral, where there are 6 of them. And they're evenly spaced around that, so they just don't impart quite as much of a change as it does when there's 6 ligands.
Okay.
And why?
I mean, it's, to be clear, it's all kind of, and this figure I don't like quite as much as the other one, but it all has to do with the the specifics of how I don't know, this is crap. The specifics of how they're oriented around those differently shaped d orbitals, right? In an octahedral, you had instances of like direct overlap between the two. And with a tetrahedral, everything being all equally spaced out, you just don't see that they can kind of wiggle between in a little bit more effectively. We still see some splitting that occurs, but it's just not a very big difference in energy that happens.
And again, why is it the 3 on top? It's just the orientation?
Yeah, so it's just the happenstance of where the orbital lies relative to the to that d orbital lobe, right? The dz squared, x squared minus y squared business. I don't have as good of a figure for that as the other one. So anyways, always high spin. So then everybody take a second and finish off this diagram for me. If it's always going to be high spin, we can fill in with our electrons here. And lastly, conclude whether this complex would be diamagnetic or paramagnetic. Magnetic. All right, so we fill it in that high spin manner where we half fill everything first before we start doubling up, and we see that this complex is paramagnetic. Okay. All right, so one more to go here. Our square planars. All right, let's take a look at, for example, this tetra bromo nickelate 2 complex here. It's got an oxidation number of 2 and a coordination number of 4. And as you may have guessed by the header, this is that square planar geometry. All right, so why is that though? It has that coordination number of 4, that is important. All right, but the other thing that tells me that this is going to prefer that square planar geometry is actually when I get to my electron configuration step. Nickel 2 has an electron configuration of argon plus 3d8, and there's just something about those d8 complexes that prefer a square planar geometry to a tetrahedral geometry. So how can we recognize that it's most likely going to be square planar? Because its coordination number is equal to 4, and that d8 electron configuration. All right, and hopefully you can kind of see where we're going here. We're going to now draw this electron configuration diagram. I'm going to kind of skip the nickel by itself, and we're just going to look at nickel 2 in our complex. All right, I'm going to be good and draw my y-axis of increasing energy. And we can note that we do see the same crystal field splitting. All right, and just like before, that splitting is unique to our geometry. So our last crystal field splitting diagram here for this square planar, we can see now has a lot of splitting going on. We have 2 lower energy orbitals, one a little higher than that, and one super high up there. All right, so first of all, just note our splitting pattern here depends on the geometry of those complexes, right? That's why we started with our geometry. All right, let me grab these boxes. All right, and we know we have to fill this in with these 8 electrons, but the question now is how? With our octahedral complexes, we had to pay attention to our ligand. Those are the worst case scenario, because then you have to figure out whether your ligand is high or low spin. For our tetrahedral complexes, we just said those are always high spin. For our square planar complexes, those are also a little bit more simple, except we're going to say they're always low spin complexes.
And then in a linear complex, would it just have that flat? Like, there wouldn't be crystal field splitting?
I don't know that for sure, but I don't think so.
Okay.
I don't see how that geometry would lead to crystal field splitting,
Fair enough.
but
So,
it could be
like,
wrong.
If we had one,
You would not have one, though. I don't know. It's just completely omitted from our textbook. So
Really?
we just gloss over the linear, I guess. I imagine because it doesn't have these cool same properties that these other ones do.
Fair enough.
All right. So lastly, if we're going to fill this in this low spin manner, we're going to go through and fully fill this lower energy level before we're allowed to move up to the next one, before we're allowed to move up to the next one. So now we've gotten rid of all 8 of our electrons, and that allows us to conclude what about this complex? It would be diamagnetic. All right, so kind of a long roundabout way to get to these magnetic properties here, but this is our crystal field splitting theory. The idea that our d orbitals, they all start out as all the same energy, but as soon as you start decorating them with ligands, those energy levels change, and that helps us to explain whether or not these complexes are diamagnetic or paramagnetic. Cool.